Hello, class. Today we just got to start a new chapter on gravity. It's going to be a really short chapter before we get to some really fun stuff about stars and supernovas, and then later on to relativity and whatnot. But I hope you guys enjoyed your long weekend and that exams went well. Looked like the scores were reasonably well for most people, so that was good to see. So we're starting quarter three now. Like I said, this little kind of mini chapter on gravity is just kind of a little chapter uh, with some background information that you're going to need to know before you need to go forward into some of the later chapters. And it's just good to know. I mean, everything in space has to do with gravity, right? That is kind of the force that governs everything we see out there, orbits, and how stars form, how galaxies form, all different kinds of things. So gravity, you guys kind of know what gravity is. All objects must fall down, and it's a pulling force. And we're gonna kind of look at gravity by how Newton explained what gravity was. And we eventually learned that Newton wasn't completely right. We didn't really get to understand what gravity truly was until Einstein figured that out about 100 years ago. And we'll talk about that later on. But mostly this chapter, we're going to talk about what Newton said gravity was. Gravity is a force of attraction between any two objects with mass. If an object has mass, that means that there's some amount of pull between them. Sorry about that. Had someone at the door, so I got a little distracted. But Newton said that gravity is a force that attracts any two objects with mass. And it really governs so much about everything that we talk about in space and everything. And gravity is a pretty special thing. It's one of the most important things in all of science and all of physics. And by extension, in astronomy. So if we, first look at, things caused by gravity. And it doesn't take a genius to understand that, things fall because of gravity. That is a force. At least Newton said it was a force that, the apple from the tree was hanging in a tree, it was at rest, and then it fell magically. Why? Because the Earth has a lot of mass, and all that mass has a tendency to pull on objects with other mass. Me and you have mass. Any object is getting pulled, is being held to the ground because of the attractive force of gravity. This is also why the moon orbits the Earth. This is what keeps people stuck to the Earth. It keeps the Earth together and doesn't fling itself apart due to its rotation. Other stuff, meteors, asteroids get pulled towards Earth, as well as, just a plane coming back to land or a rocket coming back to land. Planets in orbits around the sun, tides, which we already kind of talked about, that the ocean bulges that we've seen, the water level rise and fall in coastal areas at different times of the day. Maybe something that you didn't necessarily associate with gravity is the fact that the sun is burning. That's what causes the sun and every star to be emitting all of this light. And that's kind of a big idea of our next chapter where we're going to talk about stars, is that why do stars burn? We can see them because they emit light and they're at this really, really incredibly high temperature. That's because of nuclear fusion in their core. And as I may have already mentioned in passing, that nuclear fusion in its core is caused by that intense squeeze. There's so much mass. Objects have to have a lot of mass in order to create the pressure necessary to initiate nuclear fusion, where you're squeezing the atoms, hydrogen atoms, so much that when they run into each other, they physically fuse and create helium. That creates a nuclear fusion reaction. And in that reaction, you have mass turning into energy, and that's all the energy that our sun and every star emits. So gravity causes all of that energy. It's being radiated in our solar system. But we see the fact that planets are orbiting around the sun and moons are orbiting around us. But our whole solar system is orbiting around the center of our galaxy. And our galaxy is getting pulled towards other galaxies. The galaxy closest to us, the Andromeda galaxy, our galaxy is going to collide with Andromeda in, I forget exactly how many billions of years, but billions of years. Because these two galaxies, which right now are 2.4 million light years away, are going to, are on a collision course with each other. They're going to collide without actually colliding. But we're orbiting the sun, and the whole solar system is orbiting around everything. Later on, we'll talk about the really cool things, black holes, which are the most mysterious, nonsensical objects that exist in all of space. That's extreme amounts of gravity. That is the maximum amount of gravity. There is so much gravity in black holes that it makes a hole. It is so much gravity that space itself cannot support that amount of gravity. Thus, it makes a physical hole. There's no surface on a black hole. It's a spherical hole. And that's one of the favorite things for people to talk about. And that's why we need to do this gravity chapter, so we can fully understand more things about how stars form and how black holes form and what exactly black holes are. But black hole is the most amount of gravity that you can have, and it has so much gravity that it actually warps and bends space and time. It actually alters time itself, and really any object does. But that's stuff that's maybe a couple chapters ahead. So, and the not so obvious things like the nuclear fusion in stars, black holes, and the obvious things, that things fall to Earth, thus getting held to Earth, are all caused by gravity. So, before we can fully understand gravity, we need to understand how weird gravity is. Okay? Gravity is a force. What does a force mean? It means a push or a pull. Okay? And more so, it means to influence something. How do you influence something? You change it. When you use the word influence, that means that you are changing it in some shape, way, or form. And that's exactly what a force is. Whether that's a force that I push a little, ball across the floor. I influenced it. It was at rest, and then it started moving because of my influence. If I didn't influence it, it would still sit there, do nothing, right? But now imagine that I didn't just, push an object across the floor. That object that I was staring at it, and kind of like a Jedi Force type of thing, that I just looked at it, and I was able to make it move without touching it. That would be some weirdo magician magical stuff, right? Is that I would have this ability to move things with my mind, to move things without touching it, or without making something touching it. Yeah, you could hold a pole and push it with a pole, but that's really the same thing. Or even blowing it, you're pushing on the air, and the air is then pushing on it. But without anything actually making contact with it, think of how weird it would be if you could make things move without touching them or without making anything touching them. That's what gravity does. Okay, if I was just looking at a ball across the room and all of a sudden that ball shot across the room, that would make no sense, right? And there's only 4 forces in the entire universe that can act across a distance, that can influence things without touching them. There's only 2 that you probably really know too much about, okay? There's gravity that we see here. There's the gravitational force. There's the electromagnetic force, which is like, magnets and stuff. Magnets can influence things and push things without, moving matter, without touching them. And there's 2 other ones that exist inside the nucleus of an atom. There's the strong nuclear force, which basically is responsible for keeping an atom together, and there's the weak nuclear force that is responsible for radioactive decay. We don't really need to go into great detail about what these are, but these are the only 4 forces. These are known as the 4 universal forces. These forces exist everywhere in the universe. Everywhere that exists, these are the only 4 things that can act across a distance. These are the only 4 ways to influence objects, to force them across some distance. And gravity is one of these forces. We have a diagram of these 4 forces here. Okay, this is the strong nuclear force. It binds the nucleus. Just very quickly, you might remember from chemistry class or from physical science, what's in the nucleus of an atom? Neutrons, which have no charge, and protons, which have a positive charge. Positive charges don't like other positive charges, but they're all jam-packed together in this tightly bound nucleus. So what's keeping them together? Because if they were just left to their own devices, these positive charged protons would naturally fling themselves apart, like the 2 south ends of a magnet. So that's the strong nuclear force. The weak nuclear force is a force that in the nuclear decay, where it decays out an alpha particle or a beta particle, complicated stuff. but it exists. We don't really need to talk about it. It's kind of a long-winded explanation that we don't really need to fuss with right now. The electromagnetic force, it's kind of electricity and magnetism all in one. But that basically is the force that's the whole positive-negative thing. Opposites attract. Positive charges are attracted to negative charges. So here in this model of an atom, which is wrong, by the way, but it's useful for our purposes right now. Electrons are negatively charged. Protons in the nucleus are positively charged. They have an attraction to each other, and that's what keeps the electrons kind of in orbit, for lack of a better word, around the nucleus. And the one we focus on is the gravitational force. There's this magical attraction between any two things with mass. Even small amounts of mass will pull each other together. You could calculate the amount of force between two people sitting in the classroom. All you need is their masses and how far they are apart. In a video we were watching tomorrow, they'll even talk about two dice, like six-sided dice that you play, a board game with, something really small, that amount of mass. You place them like a centimeter apart, totally at rest, out in the middle of space. Over the course of about a half an hour or an hour, they would actually, their gravity, that small amount of mass, those few grams of mass that they have, would actually pull themselves together and they would become one. So even the smallest things all attract. Anything in the entire universe, even atoms have gravitational force. But out of these four forces, gravity is actually the weakest, surprisingly enough. But when you start talking about, crazy amounts of mass, like we see in objects in space, that force gets rather significant. But, all other things being equal, mass compared to strength of the force, gravity is by far the weakest. So, kind of the godfather of physics that everybody associates with gravity is Isaac Newton. And, Isaac Newton did a lot of amazing things in physics. He's really the godfather of really all of physics. But his universal law of gravitation basically just said that gravity is a force that extends throughout the universe that causes attraction between any two masses. We call it Newton's law of universal gravitation. Universal gravitation, that means it extends everywhere. And this idea was something called the Newtonian synthesis. The Newtonian synthesis, synthesis means to combine, to make one. And this was really the first idea that gravity extends throughout the universe, where he said the earthbound laws also apply to the heavens. And you have to think of this in the time of where he existed. And, the heavens were still held on this pedestal, and they were kind of their own thing. But Newton said, no, the same rules that we see, the same laws of science that apply here on Earth, they apply throughout everything that exists, throughout the entire universe. So he unified, he synthesized the earthbound laws and the laws of the heavens into one law, the Newton's law of universal gravitation. So very quickly, we'll just say kind of how he came to this idea. Okay, Newton understood the idea of inertia because he literally wrote a law on it, Newton's first law of motion. Inertia is that very easy principle of an object at rest will stay at rest, an object in motion will stay in motion. That just means that an object is left to its own devices, it's just going to keep doing whatever it's doing. If it's not moving, it's going to stay not moving. If it's moving with a certain velocity in a certain direction, it's going to stay moving that certain velocity. Objects don't naturally change. They don't naturally change direction. They don't naturally speed up or slow down. You need some force to cause that change in velocity. You need some force to speed something up, or to slow something down, or to change something's direction. So, the classic story is the apple falling from a tree, and Newton looked up and he saw, an apple fall from a tree. It was at rest, totally at rest, and then it moved and accelerated and fell toward the ground. He said, a force must have caused that. Something must have pulled it out of the tree. So, okay, that's gravity, okay? The earth pulls it down somehow. Well, we don't really know what it is, but a force had to cause that. I know that much. Then he also looked up at the moon. And the moon, he knows, is in orbit around the earth, going in one big, mostly circular orbit around the earth. It's constantly changing directions. That's what it means to go in a circle, is you're constantly changing directions. And he said, that also requires a force. Same reason when you turn left or turn right in a car, some force has to cause that. Something has to push you in that direction. So he said, moon's in orbit, something has to be pulling that. He realized that that force must be downward towards the Earth. He also realized the same thing for the apple. So he said, hey, that must be the same force. He did the math on it, and he realized that that is the same force between the two things. And just by that simple thought, he unified, said, hey, same things that are happening on Earth are happening in the heavens. While I'm talking about the moon, a little side note, hopefully you guys got my message on Classroom about the eclipse on late Sunday night, the lunar eclipse late Sunday night. Right now, as I speak to you, it is Sunday morning, and the eclipse is going to be tonight for me, and still in the middle of a snowstorm here, so I don't know if it's going to be clear or not out tonight. But if it is clear, check out the sky around midnight, and you should see a blood red moon. It'll be fully eclipsed. It's also going to be a larger than normal moon. That's why we call it a supermoon, and it is referred to as the super wolf blood moon, or whatever, the blood wolf supermoon, whatever you call it. But the blood moon, just because the moon appears red during a total solar eclipse, that red kind of rusty color. So that's why it's called the blood moon. Supermoon, because this is occurring while the moon is in one of its closest points in its orbit around the Earth. So it's about 7% larger than it would be on average. And the wolf moon, if you guys heard that in the news or whatever, that's just the name we give to a full moon in January. So that doesn't really mean anything spectacular. So hopefully you guys got an opportunity to check that out. Like I said, it's probably going to be super overcast because we still have this weather coming through. But kind of a neat little astronomical event for you guys to check out, or that you have hopefully checked out 2 days previous to when you're listening to this. 1 day previous, I guess. Anyways, so moon and the apple are both getting pulled by a force. He realized that must be the same force. And from there, he realized that force is gravity, and that's kind of how the universe works. So Newton realized that the moon is in orbit around the Earth, and that it's the Earth's gravity that's causing that. It is what you call a satellite. It's in orbit. That's what satellites are. Anything that's in orbit is a satellite. We have like thousands of man-made satellites in orbit around the Earth. The moon is our only natural satellite. You would say that the Earth is a satellite of the sun, and so on. So, going to kind of segue to talk about how satellites work a little bit too, or how orbital motion works. It's kind of an important idea of this little chapter as well. So, the moon is falling. All right, let me make this picture a little bit bigger for you right now. All right, maybe a little too big. So let me just focus on this picture here. So you have the Earth. The moon is in orbit around it. This picture is not to scale, of course. Now the moon, it is moving. It has motion. And on its own, it would naturally fly away in this direction. Okay? This is what you call a tangent line to its orbit. This is the path the moon would naturally take. If gravity didn't exist, the moon would have just been flung out that way after it formed, and we'd never see it again. You might remember that term tangent line from math class. So the moon wants to go this way. You'd say that the moon's inertia, kind of like momentum. Some people like the term momentum better than inertia. Not quite the exact same thing, but fits our needs for the time being. So its own momentum or inertia wants to take it this way. Why doesn't it go this way? It's because the Earth's gravity is constantly pulling it inward. So it wants to go this way, but the Earth's gravity pulls it back towards it, and pulls it back towards it. Here, the moon wants to go that way, but keeps getting pulled backwards. People always say, well, because there's no gravity in space, so you float. Wrong. If you get anything out of this chapter, understand that there is gravity in space. That's a ridiculous statement. Everything that you see in space is governed by gravity. We're in orbit around the sun because of the sun's gravity. The moon is in orbit around us because of the Earth's gravity. Gravity doesn't just magically shut off in space. It sometimes feels like you're weightless, but that doesn't mean that there's no gravity. So, is there gravity in space? Yes, 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 yes. Always yes, 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 yes. Okay? So if you get no other question right from this chapter, understand that there is always gravity in space. Anywhere that humans have ever been, wherever they look to go to, there is gravity in space. Even when you see them floating around looking weightless, yes, there is gravity there. That's a really important idea and a very common misconception. Okay, so the moon is in orbit. Now, say we magically plopped the moon right there, and it wasn't moving. Say we just, placed it 230,000 or whatever it is miles above the Earth without giving it any sideways motion. What would happen? It would fall to Earth, and you'd have a terrible, terrible collision. Why doesn't it do that? Because it's moving. It is moving in this direction. It has a very fast, what you'd call maybe sideways speed. A fancier term would be a tangential speed. But because it has this sideways motion, this motion kind of parallel to the Earth's surface, allows it to stay in orbit. The moon is falling. The Earth's gravity is pulling it. If the moon didn't have any sideways motion and you just placed it there, it would be falling right towards Earth. But because it does have that sideways motion kind of keeps it out here. And the gravity of Earth keeps it in orbit around there. So what does an object need to orbit? In order to orbit, it needs a lot of sideways motion, or what you call tangential speed. Okay, when we launch a space shuttle or a space station or a man-made satellite in space, and it orbits the Earth for weeks or months or whatever it is, we have to get it up to like 17,000 miles per hour or so. If we just placed it up there and just placed it there, it would fall right back to Earth like anything else does. At basically almost the same rate that would fall back as you dropped a baseball from eye level back towards the ground. Objects fall towards Earth. The moon is falling. It's just not getting any closer to Earth. It's falling around the Earth rather than into it. And that's a key idea. The moon is falling around. It's going at such a high rate of speed this way that as gravity keeps pulling it towards the Earth, it's making a path around the Earth rather than into it. Key idea is to understand the basics of how orbital motion works. And so we can use the moon as an example of that. So, Newton realized that the moon is falling. That means that gravity is influencing it, it's pulling it towards Earth. Usually we think falling means getting closer to Earth. It doesn't in this case. So he hypothesized that the moon is just a projectile falling under the influence of gravity. So a projectile meaning it has this sideways speed as it's flying around the Earth. It needs that sideways speed. So, satellites, as we already explained, are any objects that orbit another objects. The moon is a satellite, the moons of the other planets, the International Space Station are satellites. This number is probably a little bit higher because I made this slideshow a while ago, but all their man-made satellites, there's over 2,000 man-made satellites orbiting the Earth right now for communication, GPS, TV, radio, surveillance, spy satellites, the International Space Station, not to mention even all the space junk that's out there that's in orbit around the Earth. Get this question right. Is there gravity in space? Yes, of course there is. There always is. Otherwise, the entire universe would not work. It's a very silly misconception that people always have. That, there's no gravity in space. That's wrong. Of course there's gravity in space. More things that I kind of already said. What does it mean to be in orbit? So most people would say, oh, you're floating in outer space around a planet. Not really an accurate statement. The most important part of being in orbit is that the object is moving very fast in a direction parallel to the center object's surface, at like sideways speed, what you might call a tangential speed. Tangential meaning like tangent to. You need high sideways or tangential speeds in order to be in orbit. You can't just go up in outer space and place yourself there and expect to be floating. No, you're not floating. You're in free fall. And the question is always, you see astronauts in floating around in the space station or the space shuttle, kind of like this, you see them floating. This is actually on a simulated weightless environment, but you see them floating, and they're literally weightless. They are not tethered to the ground. They're floating in the middle of their vessel. That is not because they're weightless. That is because they are falling. What I always say is, imagine being in an elevator. You're in the top floor of a very tall building, in an elevator, and the cable breaks, and that elevator is plummeting back down to Earth, completely in a free fall. What would it feel like in that elevator? You'd feel weightless. You'd be floating in that elevator compartment. Like, oh, you're weightless, you might say. And it feels like you're weightless, but being weightless means that there is no gravity. Did gravity magically shut off in that elevator compartment for you? No, of course it didn't shut off. It's still very much there. You just feel weightless because you have no other force pushing you back up. You feel weightless because you're falling. Now in that elevator example, that falling is going to ultimately have some end to it. You're going to hit the ground and go splat, and that's going to be bad. The astronauts, however, are in a sustained free fall. They are falling around the Earth, not into it. They're going so fast sideways. We go back to this. Can't make that big anymore. But they're going so fast sideways that they are continually falling around there. So it's like that elevator example, but there's no end to it. You're just continually free falling. Gravity's still acting on you the whole time. Nothing's just holding you up. So in orbit, you feel weightless, not because there is no gravity. You feel weightless because of the lack of a support force, the lack of something holding you up. And so that's why everybody thinks that there's no gravity in space, because you see object acting like there's no gravity. But you'd see the exact same thing if you were just falling for Earth. If you jump off the building outside, or that time that you're in the air, you'd feel weightless. That doesn't mean that gravity shut off. That just means that nothing is supporting you. So feeling weightless and being weightless are two different things. Okay, there's all kinds of ways that we can make ourselves feel weightless, but we can't just shut gravity off. Okay? Not unless you went into the deep realms of space where you're so far away from anything that has any mass, would there be no gravity. There's gravity everywhere. The term we use is it's pervasive. It extends throughout the universe. Okay? So, that high tangential speed allows them to keep falling without falling into anything. So these are some of the key ideas for this chapter. Okay, so going back to the idea of how satellites work. When we launch a projectile, you throw a baseball, that's a projectile. You shoot a bullet out of a gun, that's a projectile. All objects falling under gravity follow a curved path. A path like this, it kind of curves back. If there was no gravity, it would be a straight line path and would go on forever. But gravity causes it to make a curved path and fall it down, because it wants to move this way, but then gravity keeps tugging it towards Earth. So, you give something a little bit of speed, it follows this path here, this curved path. You give it a little bit more speed, it starts following this curved path. You throw it really fast, it starts following this curved path. But what we often forget about the Earth, that the Earth is, in fact, not flat, despite what, Kyrie Irving or Shaq might say. The Earth is curved. And if you launch something fast enough, the curve of your projectile kind of starts looking like the curve of the Earth. But that speed needs to be really, really fast. And the closer you are to the surface of the Earth, the faster that speed needs to be. So most speeds that we launch things at aren't going to travel far enough to really fall around the curvature of the Earth. But as we see, if we keep throwing this faster, this curve is going to start looking more and more like the curve of the Earth. And we see that here, is that This shows up a little bit better when I animate it, but one of the classic things that Newton had on one of his original papers on this was he imagined a very tall mountain. So imagine this brown smudge here is a very tall mountain. On the top of that tall mountain is a cannon that fires a cannonball. And you put a little bit of gunpowder in there, and it takes a path like this first guy. You give it a little bit more gunpowder. You fire a little bit more vigorously. It falls more like the second guy. With more, falls like this. With more, now you see it starting to fall around the Earth. Okay, so the second to last one here, you see it starting to fall around the curvature of the Earth, but it ultimately still comes to the Earth. But if you gave it just the right amount of speed, it's going to fall and fall and fall and fall, and the Earth's going to keep curving away from it. The Earth's going to keep curving and curving and curving away from it, and it's going to go all the way around the Earth and come back and hit the cannon in the back of the cannon. Or, this is some magical bazooka gun, and come back and hit the person in the back of the head. It would do a full lap around the Earth. And it will keep doing this forever, as long as it's above the Earth's atmosphere. People also say, well, above the Earth's atmosphere, there's no gravity. That's a lie. The only reason that we need to have satellites orbit above the Earth's atmosphere is because above the Earth's atmosphere, there is no friction. Air resistance would slow this down. In order to maintain this orbit, the object has to be moving really fast. And if it's interacting with the air, that's going to slow it down. And at these speeds, 17,000, 18,000 miles per hour or so, that would be enough speed to kind of make it turn into a fireball. There'd be so much friction, that'd be slowing it way, way down that it'd generate all this heat. But objects in orbit are just continuously in a free fall. They're falling. They're just never falling into anything because of that really fast sideways speed. And again, here we see a satellite around the Earth. The satellite wants to go in this path. Its natural motion wants to take it in a tangential path. But the Earth's gravity pulls it inward. So those two things are kind of at right angles to each other, and no matter where it is, when the satellite's up here, it wants to go that way. But the Earth's gravity keeps pulling it back towards the center of the Earth. So, again, we've already defined a satellite. They're just projectiles that fall at the exact same rate that the Earth or another planet curves away from it and never reaches the surface. Now, satellites don't need to be going at the exact same rate exactly. They can be going faster or whatever and take a more elliptical orbit. And they don't always have to be perfect like that. But they do have to be going fast enough to achieve an orbital speed where they won't eventually start curving, get closer to the Earth, then start hitting the atmosphere, and then that's going to slow them down and all that kind of stuff. So, some fun hypotheticals that we like to pose. 1. An object was placed at rest at the altitude that the International Space Station, which is a satellite, is at. It's only 250 miles above the surface of the Earth. In the grand scheme of things, not very high above the surface of the Earth. That's like the width of Ohio, the east to west distance of Ohio maybe, above the surface of the Earth. So what if we just placed an object and plucked it and put it up at that altitude and gave it no sideways speed? This could be a multiple choice question on a test. Is it going to fall back to Earth? Is it going to float there in outer space? Is it going to fling deep in outer space for some reason? Is it going to fall back to Earth at the exact same rate as it does if it were close to the surface of the Earth? Or maybe a little bit slower than that? The answer to this question, some people might say, oh, it would be float because it's in space. And that would be wrong. The object, as you guys can see, the object would fall back to Earth at a rate a little bit slower than things accelerate at the surface of the Earth. This is the rate of acceleration at the surface of the Earth. It would be very near that because you're not that far away. So it might be like 9.6 meters per second squared. Okay, this is not that far away from the center of the Earth. So it would, it would fall back to Earth, much like anything else, at a rate just a slightly smaller rate than it would be if that same object were placed just a few feet above the surface of the Earth. Second hypothetical. An object was placed at rest at the altitude of the Moon. Way, way, way further away. 240,000 miles away from the surface of the Earth. What's going to happen to that object? Is it going to sit there and float? Is it going to fling away? What's it going to do? It's still going to fall back to Earth. It's just going to be at a rate, initially at a rate, much less than the rate that things fall back to Earth when they're close to the surface of the Earth. But it will fall back to Earth if it were at the distance that the moon is, which is pretty far away. Okay? So, again, there is gravity in space. So, a few things about man-made satellites. We currently have this many orbiting the Earth. That number's probably gone a little bit up, but 2,271 satellites orbiting the Earth. Many tens of thousands pieces of orbiting space junk for missions, pieces of missions, and all other kind of junk that we leave up there. Don't want to get hit one of those. If you ever saw the movie Gravity with George Clooney and Sandra Bullock, you know that those things can be a problem because each of those pieces of orbiting space junk are all moving at 17,000, 18,000 miles per hour or so. And if one of those gets in the way of astronauts or a space station or some important mission, it's going to shred right through it at 17,000 miles per hour, which is an absurdly fast speed. It's like Mach 30 times the speed of sound or so. Okay, a few more things before we finish up here. So, we already mentioned Newton's law of universal gravitation. There's an equation here. This is astronomy class, though, so we do not like equations. But I at least want you guys to look at it. So, Newton's law of universal gravity says this. The force of gravity acting between two objects is directly proportional to their mass and inversely proportional to the square of the distance between them. Wow, that's a mouthful. But this equation basically sums that up. This represents the force of gravity. This is the mass of one object. This is the mass of a second object. This is the distance between them squared. This big number, this number with the capital letter G, that is a constant. This is the universal gravitation constant. That number is always this number, 6.67 times 10 to the negative 11th. That's written out, would have a value of 0 with the decimal place, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, 667. That is a very small number. So what does that say? If this is a really small number, and this is getting multiplied by the two masses. So really small number here, two masses here. So say this is my mass, we'll say 90 kilograms, and a student's mass, 70 kilograms. So 90 times 70, well, that's what? 6,400 or whatever. Or whatever that is. I can't multiply in my head right now. But that's still not that big of a number when you're looking at how small of a number this is. Okay, so 90 times 70, 6,300 via the top, then multiplied by this number, that's a super small number. So the fact that this number here, this big old G, is this tiny thing, tells you that unless these two masses are really, 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 really big, this is not going to be significant at all. So you can calculate the gravitational attraction between two people in the room, but that number is going to be so small it winds up being what you call negligible or insignificant. But when these two masses become big, say the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, multiplied by my mass, 90 kilograms, then you multiply that by this, that winds up being a noticeable number. But we still have to multiply the distance between the two objects. Okay, so we don't need to worry about doing this equation. We need to do about doing the proportions of it. Force, this number is directly proportional to the masses. It's inversely proportional to the square of the distance between them. So, what this law means is whatever factor the mass is increased by, the force of gravity is increased by the same amount. So say if my mass was triple what it is, that means the force of gravity would also be triple. That's what it means to be proportional. If you have twice as much mass, you're going to have twice as much force. You have 10 times as much mass, you're going to have 10 times as much force. Proportional to doesn't mean equal to. Proportional to means related to. So mass and the force of gravity are real simple. So I might ask a question, how much harder does the Earth's gravity pull on a 200 kilogram object than a 100 kilogram object? You'd say twice as much. There's twice as much mass. That means that Earth's gravity is going to be pulling on it twice as much mass. That's the easy part. The hard part is the second part, is that the inversely proportional to the square. So whatever factor the distance between the two objects is increased by, the force of gravity is multiplied by the inverse of the square of that number. So that means if the distance between two objects is tripled, that means the force of gravity is 1/9 as much. So that means, so right now, as I stand here on the surface of the Earth, I'm about 4,000 miles away from the center of the Earth. Okay? And let's just say, to make it a nice round number, my weight in newtons, how hard gravity is pulling on me, is 1,000 newtons. So when I'm 4,000 miles away, gravity pulls on me with 1,000 newtons of force. Say I magically go to twice as far away from the center of the Earth as I am now. So I go 4,000 miles further away from the center of the Earth as I am now. So I doubled the distance. That means that the force of gravity on me is going to be 1/4 as much. It's going to be to 250 newtons. It went from 1,000 to 250. So some examples of that here. Make this font a little better so you guys can see it. So, force of gravity acting on an object while on the surface of the Earth is 1,000. What would that be on you if the Earth's mass magically doubled? Force and mass are proportional, so it would also double. What about if your mass doubled and the Earth stayed the same? Again, force is proportional to mass, so the force would also double. But kind of like the example I just explained to you, is what would the force of gravity acting on you be if you were twice as far from the center of the Earth as you are now? That means that your force would be reduced by a factor of 1/4. Okay? Inverse square proportion. The distance changed by 2. What's the inverse of 2? 1/2. What's the square of 1/2? 1/4. So, it's a little bit better explained when I'm there in class, but this slide basically is probably the easiest way to understand this. We're not going to have to plug all these numbers in this equations and do things like this. But we are going to have to be able to do things like this. By whatever factor the distance changes, the force is going to change by the inverse square of that amount. Inverse means flip it. Square it means multiply it by itself, right? Here's another example. So say a spaceship with a weight is another term for force of gravity, by the way, of 10,000 newtons on the surface of the Earth. That moves to a distance that is 3 times further away from the center of the Earth. So it went from here all the way to here. It's a distance of 1, 2, 3. It tripled its distance. So, as you see, scooch that up so you can see. So the distance is increased by 3 times. So the force of gravity decreases by the inverse square of that number. So the force of gravity is going to go down by 1/9. So you'd multiply it by 1/9 or divide it by 9 would be the same thing. So just by increasing its distance by a factor of 3, the force of gravity in the ship went from a force of a very large 10,000 to a much smaller 1,111.1 newtons. And here's a graph that kind of sums that up. How the force of gravity changes with distance. Double the distance, it's 1/4. Triple the distance, it's 1/9. 4 times the distance, the gravitational force is going to be 1/16th, 1/25th, 1/36th, 1/49th. So very rapidly with distance does the force of gravity decrease, but it never fully goes away. This line is never going to fully get to 0. You can wind up being so far away from an object that the object is 0.00000000001 or whatever, and get so small that it becomes negligible, but it can never be 0. That's why we say that gravity is pervasive. Okay, so it's about 45 minutes right there, so I'm gonna wrap this up. There'll be a few other short videos that I give you this week of me talking and lecturing to finish this up, as well as some ones from YouTube that give you a little bit more interesting look at what gravity means. There'll also be a fill in the blanks worksheet that will be passed out at some point this week. So hopefully you guys are paying attention to fill in those blanks. There'll be a short quiz over gravity by the end of next week.